Ignition and liftoff of the Space Shuttle Discovery, returning to the space station, paving the way for future missions beyond.
On March 17, 2018, UK wind farms were producing almost 40% of the power in the national energy grid. With a combined output of 14 gigawatts, this was more power than the combined total power of the liftoff configuration of the Space Shuttle, and all from the wind. Wind power is becoming a significant source of global energy production, and as energy storage techniques continue to improve the consistency of power from this resource, it is only going to grow in importance. However, megawatt turbines like the ones used in offshore wind farms are huge and expensive pieces of infrastructure, so in order to test new and innovative design features, we need a cheaper alternative, and one that can be tested in a controlled environment like a wind tunnel. This is where our project comes in. But how exactly do wind turbines produce their power?
Elementary, my dear Holmes. Elementary.
As wind flow passes through the turbine blades, a lift force is generated on each blade, which causes the blades to rotate. This rotary motion then drives the main shaft, which is connected to the generator, and which converts kinetic energy into electrical energy. The coefficient of power is a useful parameter for us to measure the performance of our wind turbine. Cp is defined simply as the ratio of electrical energy produced by the turbine to the total kinetic energy of the incoming air. Simply put, the larger the Cp value, the better performing and more efficient the wind turbine.
Another important quantity to note would be the tip speed ratio, or TSR for short, which is basically the ratio of the tangential speed of the blade to the incoming wind. Too low a TSR might result in stalling, whereas too high a TSR might be an indication of inefficiency.
Design's a really loaded word. I don't know what it means, and so we don't really talk about design a lot around here.
For the design of this turbine, we were provided with a number of constraints. Firstly, the turbine should rotate clockwise when viewed from upstream, not exceeding 3000 RPM at a wind speed of 12 meters per second. Furthermore, the TSR must be between 3 and 8. The blade must also be manufacturable as one single part and be able to fit in a box of length, depth and height of 400, 75 and 150 millimeters respectively. Moreover, the hub of the turbine was specified and to be manufactured out of aluminium. Bio-inspiration or originality was also desirable. The turbine was to be tested at 4 different speeds, 6, 8, 10 and 12 meters per second. The objective is to achieve the maximum power coefficient in this range. After exploring a range of different hinge designs, we chose to use 2 ball-and-socket hinges to connect both parts of the hub together. The simple design, which comprises of simple geometric shapes of 2 spheres and a cylinder, made it relatively easy to model and create. Furthermore, the ball-and-socket hinge would be hidden within the hub in the final turbine assembly, and as a result, would not affect the flows around the hub. Although the blades are rotating at the same angular velocity, the further that section is from the hub, the greater the speed at which it is spinning. As a result, different parts of the turbine experience different incident air velocities in terms of both speed and direction. In order to maximize the efficiency of the blade, we twisted and tapered our turbine blades from the root to the tip according to the angle of attack, which maximizes lift and minimizes drag for each section. The nose cone plays an important part in the performance of the turbine. Hence, we used the formula governing the Hack series shapes for nose cones developed by Wolfgang Hack to determine the optimal shape. 3 screws were used to join both halves of the hub together securely. However, in order to have sufficient surface area to fit the thick blade roots and screws, we had to compromise for a more blunt nose. Using existing research data on airfoils for small horizontal axis turbines, 3 types of airfoil were shortlisted based on the operating Reynolds number and lift-to-drag ratio. These were the SG6040, SG6042 and SG6043 airfoils. The airfoil profiles were obtained from the UIUC airfoil database and were used to recreate the airfoil in Korea.
So now we need to determine which airfoil to use in our turbine blade. First, we calculate the optimal core length and pitch angle for each airfoil using the Schmitz formula. The Schmitz formula is dependent on the size of the turbine blade, TSR, and the performance of airfoil. Since the size, angular velocity, and wind speed is fixed, 3 airfoils would give 3 different core length and pitch angle based on their maximum lift-to-drag ratio and the corresponding angle of attack.
with the core length and pitch angle, we can apply blade element momentum theory, or BM for short, as shown in this flowchart. BM theory is an iterative algorithm used to calculate load and therefore power along a turbine blade. We use MATLAB to apply this theory. From the BM code, we can plot load along blade for the 3 airfoils as shown in this figure. From the figure, we can see that SJ6042 has best overall performance, hence we have chosen it as our main airfoil. For the root of the blade, we have chosen SJ6040 as it is thick and has larger stow angle. Using MATLAB, we found that blending the SJ6040 to the more aerodynamic SJ6042 at 20% blade radius was a strong compromise to maintain structure integrity and performance.
Wind turbine blades experiences large aerodynamic and centrifugal forces under high spinning speed. There are 2 criteria the design structure must fulfill. First, the stress in the structure should not exceed the critical stress of the building material, so the structure will not fracture during the test. Second, the blade tip deflection should not be excessive. Excessive deflection would induce severe vibration which may damage the structure. By approximating the wing as a simple beam and applying simple beam theory, we estimated the centrifugal forces, tensile stresses, and bending moments along the blade on MATLAB. Our analysis shows that the tensile stress is much greater along the spar than along the cord. In this project, we are using rapid prototyping to print our turbine blade. 3D printing plastic is non-isotropic. The peak failure stress in the transverse direction is smaller than that in the longitudinal direction by approximately 20%. Hence, we decided to align the transverse printing direction with the cord. The calculation shows that the maximum stress in the structure lies safely within the limits of 32 megapascal. The wing tip deflection is also found to be minimal overall.
Since this turbine was going to be tested over a range of different wind speeds, we wanted to introduce an original design feature that would improve the off-design performance of the blade. Using the pressure difference between the leading edge and upper surface of the blade, air is drawn into the center of the blade into a plenum, or reservoir. The pressure then expels this air through angled jets on the upper surface. But don't take it from me, take it from a man who wrote a thesis about it.
So I'm Andy Oliver, I'm the Chief Technology Officer for RES Group. We build wind farms, solar farms, battery energy storage projects based in 10 countries around the world. So the idea was to take air jet vortex generators, which are similar to vanes when you look out the window of an aircraft and see these vanes sticking up in the air above the wing. The idea is to blow air out, train a vortex around that air that was ejected, and that would re-energize the boundary layer of the wind turbine. So I was down the lab one day, and up to this point the concept had been to forcefully inject air into the plenum in the middle of the blade by means of a pressure device, so that you would have had to have active power, blade power from the actual wind turbine itself to power this thing. But I was sitting there and thinking, we've got a low pressure side of a blade and a high pressure side of the blade. What if we connected the two together so that the air bled through from the high pressure side to the low pressure side? That was a breakthrough because it magically works. Another challenge is how do you control these jets, right? You don't necessarily want them blowing the whole time. In an ideal situation, you just turn these on as you approach the knee of the power curve in the wind turbine. Then to actually manufacture, I think you've proven that you can do that, but obviously it creates stresses in the blade locally where you've made the holes. That's a challenge to overcome.
The main blade was printed from ABS plastic with the central hub machined from aluminium. Once printed, the blade was unfolded and bolted on together with 3 bolts, and then securely fastened to the central hub with a pin. We then sanded the entire turbine to obtain a better surface finish. However, we found out that there's a defect in the printing which caused one of the blades to deflect slightly more than the other. Although we attempted to fix this with a heat gun, the asymmetry could clearly be seen during our tests.
They don't just tell the bits, they put them to the test.
Our blade was tested at 4 different wind speeds, with the results shown on screen. Our peak power was 153 watts at 10 meters per second, and our peak CP was 0.56 at 8 meters per second. This peak CP happened at a TSR of 8.55. Note that beyond 10 meters per second, the blade began to stall catastrophically, which made a noise like this.
Oh, that's beautiful. Goodbye, blade.
At 12 meters per second, the blade was completely stalled, as shown by the low power CP and the power curve. By covering up the vortex generator jets with a piece of tape, we are able to qualitatively evaluate their performance. We concluded that they did improve the off-design performance of the blade by delaying the catastrophic stall when they were open and working.
Actually, one of my early projects was on blockage corrections, and that's my final year project. And we had a closed tunnel versus an open tunnel, and the idea was to try and balance those two opposing corrections out. Fortunately, I didn't end up doing that because it was really boring, and ended up doing this wind turbine stuff instead.